Most of the time when we study wavelet transforms, we focus on the case of a one-dimensional signal. That is usually a time series where you have some discrete series of recorded signals at time equals 0, 1, 2, up through n-1. So we learn a lot about how to deal with those. And the question that I'd like to explore in this video is how do we use that knowledge to do wavelet transforms on two-dimensional data, for example, on images as opposed to sounds. The good news is that there's not that much to do in that if you understand the one-dimensional case, the two-dimensional case is fairly straightforward. So let's go ahead and explore how that works. So let's take a look at the surprisingly pleasant world of two-dimensional wavelet transforms. So the starting point is we understand how to deal with one-dimensional signals. Typically these we imagine are maybe sounds where at time k we imagine this is the strength or maybe amplitude of the sound signal. For two-dimensional signals we might imagine that we're thinking about images, for example, given in grayscale, where at any given coordinate, say with x coordinate j and y coordinate k, we have some particular value or level on the grayscale between black and white. Now, one-dimensional signals we typically represent as vectors. So we imagine them as typically column vectors, just a list of the signal at different time values. Two-dimensional signals are often represented as matrices. So a matrix, I mean, although we often think of it in terms of matrix algebra and multiplication, we're really thinking of it in this context as simply a convenient way of representing a two-dimensional array of data, so that the jkth coordinate of the matrix represents the signal at x value j and x value k, I guess, and y value j. And so this is really just another way of representing the vector space, which is an n-squared dimensional vector space. So, so then the plot is, we suppose we know about how a one-dimensional wavelet transform works. That is, we're given some explicit matrix, the analysis matrix T sub A, which we think of as taking the signal x and giving us back the trend and the detail vectors. And we'd like to know, how do we take this linear transformation, TA, and get some new, like, 2D version of A, which will go from C to the n squared to C to the n squared? And what will be the kind of two-dimensional trend and detail that one would get from that? The basic idea of the two-dimensional wavelet transform is just going to be to apply the one-dimensional wavelet transform first to every vertical strip and then to every horizontal strip of, for example, the image. So what does this look like? So the basic structure looks something like this. We imagine that we start with the signal z, which we think of as some big matrix. We apply the wavelet transform vertically first to each of our columns. Now that means that we get a new matrix that we can think of as broken up vertically into two parts. So the top of the matrix, each of the columns of the top of the matrix represents the trend of one of the columns in the original matrix. So I'm denoting that by V for vertical and TR for trend. And then on the bottom part of the matrix, these little strips of half the full size vertical strips represent the detail vectors of each of these vertical strips in the original matrix, each of the columns in the original matrix. So I've written this as V detail for the vertical detail. Then what we do is we do the exact same thing to the rows of the matrix that we've gotten after this wavelet transform. When we do that, we get a matrix that really splits up now into kind of four parts. The top part is broken up now horizontally as the horizontal trend of each of these rows and the horizontal detail of each of these rows, the horizontal trend of each of these rows, and the horizontal detail of each of these rows. So the two-dimensional transform then takes our matrix and gives back a matrix which now has four parts to it. the horizontal trend of the vertical trend, the horizontal detail of the vertical trend, the horizontal trend of the vertical detail, and the horizontal detail of the vertical trend. A little bit of a tongue twister. You might wonder, well, what if I did first a horizontal and then a vertical wavelet transform? Like, why am I doing the vertical first? Why not the horizontal first? Turns out, fortunately, for those who don't like to make these difficult decisions, it doesn't matter. You get the same answer either way, which we'll observe in a bit. So how does one then interpret these matrices? So as I said, it's broken up into these 4 quadrants. So the thing on the top, this is just the averages of the averages in some moral sense. And so we can really think of this as the trend. It's the trend in every sense. On the other hand, let's take a look at this entry here. So this is the horizontal trend of the vertical details. So what does this mean? We've kind of averaged out the horizontal stuff, and we're seeing how things change vertically as we move vertically. So that means that what we're seeing is if there's some change as you shift vertically, but we're not, where everything is kind of smeared out horizontally, what we're actually seeing is horizontal features, right? If things kind of, if there's like a line going across so that you kind of have a little discontinuity, that's where, this is the quadrant of that matrix where that's going to be picked up. Similarly, this other entry is picking up the vertical features, the vertical trend of the horizontal detail. So you smear things out vertically and you see how things change in these strips as you move over to the right and the left. That picks up vertical features. And then the final entry here detects change when both the horizontal and the vertical move. And what is that? That's the diagonal features, the features that kind of, you know, things that change as you move diagonally. All right. So this is all well and good conceptually, but from a practical point of view, how do we express this transformation in terms of matrix operations? How do we express, excuse me, how do I get back? How do we express going back from this process of taking a matrix like this and getting a matrix like that? So that's the next thing to consider. In order to see how to efficiently describe this process of acting on both the rows and the columns with these wavelet transforms, we're going to first start with a little bit of linear algebra and think about matrix multiplication in a slightly different way. So let's go ahead and do a little bit of linear algebra. Let's imagine that we're trying to multiply 2 matrices together, but I'm writing one as just an abstract matrix T, and I'm writing the other in terms of vertical strips. So these are both n by n matrices, but I'm just thinking about this one as being broken up into a bunch of columns. So matrix multiplying T by this matrix, thought of as a series of column vectors, is actually the same as applying the linear transformation T successively to each of the columns, thought of as vectors, as column vectors. And so this is kind of an exercise that you might do if you haven't seen it before. Just work out that this is actually what matrix multiplication is and does. Now, if you had a matrix that was a bunch of, that you wanted to think of as a bunch of row vectors, how would you affect doing the linear transformation on each row? It turns out that, not a surprise perhaps, that the transpose on the other side is the thing responsible for that. Not a surprise from the point of view that, you know, transpose reverses the order of multiplication, so it should go on the other side, and it also switches rows and columns. So it's easy to see that this actually holds by taking taking the transpose out. So I can kind of pull out a transpose that turns all these rows into columns, and this is just another way to rewrite it. Now, if you use the above expression, then that's the same as just acting on each of the columns. And finally, if I then apply that transpose once more, you can see that each of these columns is going to turn into a row, because that's really what the transpose does. And so that's a nice way to think about how to apply a linear transformation to either the columns or the rows of a matrix. If you want to apply the linear transformation to the columns, you multiply on the left. If you want to apply it to the rows, you multiply on the right by the transpose. And this is exactly what we wanted to do with the two-dimensional wavelet transform. So if we're thinking about this process of the wavelet transform, we're going to be taking our Z. Now Z we're thinking of as a matrix. It's an n by n matrix. But if I left multiply it by the analysis matrix, what does that do? It applies the wavelet transform to each of the columns. And so the TA on the left times Z is the vertical or column wavelet transform. Similarly, if I applied TA transpose on the right, that's the horizontal or row wavelet transform. And finally, if I wanted to do it at both sides at the same time, we get the two-dimensional wavelet transform by sandwiching our Z with a TA on the left and a TA transpose on the right. And here is an interesting part that we can make a comment that it doesn't matter which order you do this with. Because of associativity of matrix multiplication, if I do this product first versus if I do the other product first, I get the same answer. This is just associativity of multiplication. Now, finally, you put these things together, and this gives us the this two-dimensional wavelet transform that breaks up, that takes a matrix Z and outputs this matrix that you can think of as a bunch of blocks corresponding to the trend, detail, trend, detail parts of our two-dimensional transformed signal.